Hi all, let us derive EMF equation of DC machine today. As we know, DC machine while operating like a generator depends on Faraday's laws of electromagnetic induction. So what is Faraday's law? Whenever a conductor is moving in a time invariant magnetic field, it experiences changes in flux linkages so that EMF will be induced. Now I'll slightly modify this Faraday's law and apply it to the current DC generator. So let us say whenever a conductor of length L, let us say the conductor is having an amount of length L. So L is the length of the conductor which is moving with a velocity V inside a time invariant magnetic field which is denoted by the flux density B bar. So the total amount of EMF induced in this case is E is equal to BLV sin theta. So what is theta, sir? Theta is the angle between conductor movement and the flux linkage. So we assume that always the conductor movement and flux linkage angle is maintained at 90 degrees because this depends upon the construction. So theta 90 means what about E? E is equal to BLV sin 90. So BLV sin 90, it is given as sin 90 is 1, so BLV. So this is the amount of EMF induced in a DC machine for one conductor. So therefore I can write the unit as volt per conductor. Volt per conductor. Now I will now assume that the total DC machine has P number of poles. So let us assume that the DC machine what we have taken has P poles, and in these P poles let us say the flux developed per pole is phi. So phi indicates flux per pole. So therefore what is the magnetic field density B? B is given by total flux per area. B is given by total flux per area. So total flux is how much? See, for one pole that I am saying phi amount of flux because flux per pole. So likewise I am going to have P number of poles. So that's why the total flux is phi into P by what is the area? While coming to the area, lot of people have misconception what is area. See, area means here total lateral surface area because you are assuming circular conductors. Actually they are cylindrical conductor. These circular conductors are of length L. So let us say the circular conductor is having a radius of R and of length L. So these they'll move like this. They'll move like this inside the magnetic field. So therefore, what is the amount of total area occupied by this? That is 2 pi RL. That is 2 pi RL. Once again I am drawing here. See here we assume circular conductors each having length L. So circular conductors having length L. These circular conductors rotate like this inside the field. So therefore I can say the total area is 2 pi RL. Okay. So therefore what is the flux density experienced by each conductor? Therefore I can write flux density experienced by each conductor. Experienced by each conductor. Okay, let us say radius R. Flux density experienced by each conductor, that is B. How much? P phi by 2 pi RL. But we require induced EMF. So induced EMF is given by what? We have seen in the top, induced EMF is equal to BLV, where B is magnetic field in flux density, L is length of the conductor, and V is the velocity with which it is moving. So I'll substitute all the values here. So B is given as here from the equation. Using this equation I can write B. So B is P phi by 2 pi RL into L is the length of the conductor and V is the velocity. So therefore I can cancel the common terms. Here L is common. So therefore I am getting induced EMF. I'll show with the letter E. E is obtained as P phi by 2 pi R into V. So this is the EMF per conductor. Okay, this gives EMF induced per conductor which is traveling in a magnetic field of B, flux density B, and with velocity V. So EMF per conductor. So based on this formula we have once a gate problem also. So try to search for it. So P phi by 2 pi R into V. But if you observe, generally our conductors follow circular motion like this. But V represents linear velocity. V represents linear velocity. So this linear velocity must be converted to omega. Omega is angular velocity in radians per second. Linear velocity has units of meters per second and angular velocity has units of radians per second. So therefore we assume that, or we infer that our conductors are moving in circular motion like this. So therefore it obeys projectile motion, and hence the velocity is angular velocity in radians per second. So how to convert? We have a relation. So V is equal to R omega, where R is the radius of the path you have taken. So that is also we can easily derive. So let us say our conductor is moving from position A to position B like this. Okay, if this is the arc formed and this is the length of the arc, we can easily write L as the length of the path traversed and R is the radius, and with theta angle it has made while traveling. So L is equal to R theta. This is the famous formula. From this I can write dl by d theta is equal to R into, sorry, once again, L is equal to R theta I can write here from the basic geometry, length of the arc. So dl by dt, if I do the derivation on both sides, R into d theta by dt. dl by dt, the shortest displacement between the points A and B here. So therefore it is your velocity. So R into this d theta by dt is angular velocity omega. So this is the formula we can derive for relation between linear velocity and angular velocity. So therefore if I substitute in the EMF induced here, I am going to get induced EMF E is equal to, so what is the equation we obtained earlier? We obtained E is equal to P phi by 2 pi R into V. So in the place of V, now I am going to replace V with R omega. So therefore I am going to get E is equal to P phi by 2 pi R into R omega. If I cancel common terms here, R is in common. So this is the total amount of EMF induced per conductor if your conductor is rotating with an angular velocity. The above obtained equation is the total amount of EMF obtained if your conductor is moving in linear velocity. So but we have n number of conductors. So in general in DC machines we will indicate Z as total number of conductors, and A as total number of parallel paths. So for better understanding, what I will do is I will take 12 conductors. So I'll write here, let us wait. So I'll assume 12 conductors arranged in two parallel paths. That means now look here, I'm going to have the configuration like this: 1, 2, 3, 4, 5, 6. So all these are 6 conductors, let us assume, in one parallel path, and another 6 conductors in another parallel path. Okay, so for each parallel path, let us say there is E amount of EMF induced. For each parallel path, let us say there is EMF E induced. So this is the total amount of EMF induced for each parallel path. So generally your parallel paths are represented like this. So that the total amount of EMF now induced across this entire configuration, EG becomes 6E, because for each parallel path 6 number of conductors are arranged. For each conductor E amount of EMF is induced. So therefore for this parallel path 6E, and for this parallel path the amount of EMF is induced is 6E. If you observe properly, the parallel paths will always be connected in parallel. That's why they are called parallel paths. In parallel, what will be same? Voltage will be same. That's why EG is always 6. This EG, now I am going to write this EG as 6E directly, but the 6 I am going to replace this 6. Instead of 6, what I will do is I am going to replace the 6 with 12 by 2, because 12 by 2 is always again 6. But what is 12 here? We assumed what is 12? 12 is number of conductors, 2 is number of parallel paths. So therefore number of conductors generally given by capital Z, and number of parallel paths is generally given by capital A in DC machine terminology. So therefore the total amount of EMF induced EG can be written as Z by A into E. Now coming to the topic, EG is equal to, I have the EMF equation as, for one conductor we have P5, let us indicate with small e, So E is equal to P5 omega by 2 pi. That is for that is called voltage obtained for conductor or voltage induced for conductor. But all these conductors are Z, and these Z number of conductors are arranged in A number of parallel paths. So therefore total EMF induced can be written as Z by A, because Z number of conductors arranged in A number of parallel paths, into P5 omega by 2 pi volt. But speed, here omega is angular speed, but generally we will be given in RPM in numerical problems. So we should know the relation omega is 2 pi n by 60. Omega is 2 pi n by 60. Therefore Eg is equal to, if you replace omega, you are going to get Z by A into P5 into, in the place of omega I am going to substitute 2 pi n by 60. 2 pi n by 60 whole divided by, so already 2 pi is there, so I can cancel the common term 2 pi here. So now I am going to cancel 2 pi. So what is the relation I am getting? Therefore Eg is equal to, I am going to get Z by A into P5n by 60. So this is a different approach, I hope, for deriving the EMF equation of a DC machine. So far in different books you have seen a common procedure, but with slight modification you are going to derive the EMF equation in this manner, which is valid for any case. Thank you.